Soul should always stand ajar, ready to welcome the ecstatic experience. A very good morning and welcome to one and all present here, Honorable Principal Madam, esteemed panel of judges, respected Supervisor Madam, faculty members, and the fellow participants. I am Meenakshi Das, and it is both an honor and a privilege to stand before you and welcome you to the seminar. It is believed that Lord Ganesha clears all the obstacles coming in our paths. So let us take a moment and pray to Lord Ganesha that he makes this event successful and blesses all of us.
वक्रतुण्ड महाकाय सूर्यकोटि समप्रभा निर्विघ्नं कुरु मे देव सर्वकार्येषु सर्वदा.
It gives us immense pleasure to extend you a very warm welcome on behalf of DAV Public School, UNIT-VIII, as we have come together for the mathematics seminar of the session 2021-22 on this virtual platform. And the topic for today's seminar is graphs of different functions. I extend a very warm welcome to our beloved principal ma'am. We extend a warm welcome to our honorable and esteemed panel of judges, Mr. Amyaranjan Mohanty sir from DAV Public School, Kalinganagar, Mr. Sai Shankar Acharya sir from DAV Public School, Pokhriput. I also extend a warm welcome to Supervisor ma'am, teachers, and the audience. So, before starting, let's have a briefing on the standing rules or the guidelines of the seminar, which I request all the participants to abide by positively. Number one, each participant will be given a total of 5 minutes to present, followed by question-answer session by the judges. Number two, it is mandatory for all the participants to keep their audio and video on positively during the presentation. So, without any further ado, let's move on with the presentations. I just can't wait to see what our fellow mates have put forward for their presentations in the light of the topic, graphs of different functions. So, shall we start? Let us call upon our first participant of the day, Anirudh Pradhan of class 12, section E. His topic is graphs of exponential functions. All the very best, Anirudh. So Anirudh is having some technical issues. So let's move on to the next performance. Let's call Anjali Mishra of class 11A and see what she has to tell us. Over to you, Anjali. Good morning, everyone. Is my audio, video, and screen visible? Hello, am I audible? Hello, am I audible? Yes, you're audible, Anjali. Okay. Maths is not simply about a domain of innocence, but maths is a whole new world with relations and functions. Can you speak a bit louder, Anjali? You're audible very faintly. audible now? Yes, speak a bit louder. There's some problem in my audio. Hello, is it audible now? Yes, it's audible now. Okay. So maths is not just a domain of different integers, but maths is a whole new world of relations and functions. With this note, a very warm morning to everyone present over here. Honorable Principal Ma'am, esteemed judges, my fellow contestants, revered teachers, and all my dear friends. This is Anjali Mishra, a student of 11A, and I am here to present my seminar on the topic, smallest integer function. Well, when I say about functions, then I refer to a special kind of relation. And out of those, smallest integer function is a very special relation. It is defined as such: a function f of r in R is a function of the least integer that is greater than or equal to x if and only if for all value of x belongs to between n to n plus 1, excluding the value n, and the smallest integer function is n plus 1, where n is an integer and x is a number which is greater than n but less than or equal to n plus 1. This is called a smallest integer function or least integer function. The other names for least integer function is ceiling function or step function as well. We can understand this with the help of an example. Let's take a number 0.5, and the smallest integer greater than or equal to 0.5 is 1 itself. For getting to know the other examples, if we take a number 2.3, then the smallest integer function is 3. If we take a number minus 3.2, then the first integer coming to the right side when represented in a number line is minus 3. If we take a number 4, then the smallest integer function remains as 4. We can also see a table where I've compared between the flow and the ceiling function. If we take different values as such like minus 2.7, then the ceiling function is minus 2 and the flow function is minus 3. Now, from the very definition of smallest integer function, we have, if we take a number x, which is greater than 0, but less than or equal to 1, then the smallest integer function is 1. If we take a number x, which is greater than 1, but less than or equal to 2, then the smallest integer function is 2. If we take a number x, which is greater than 2, but less than equal to 3, then the smallest integer function is 3. So on, if we try to plot it in the form of a graph, we will find that it resembles the appearance of a staircase, and so it has been named as step function. We can also see that there is a loop at the end of every previous number, because if I take two numbers, 1 and 2, then the smallest integer function of any other number which is coming between 1 and 2 will be 2, excluding the value 1. As we are excluding the value 1, there is a loop or a kink made at the point 1. Likewise, we can also see the other graphs where it is evident that smallest integer function is a kind of a step function. Moving on to the domain of smallest integer function and the range of smallest integer function. When I talk about domain, then I'm referring to all those possible values of x for which I'll be having y as an output. So the domain of y is equal to x would be all the real numbers, because we can substitute any number in place of x and we can get a result. We can also see some examples in the bottom. If I take a number 3.5, then the smallest integer function would be 4. If I take a number minus 4.6, then the smallest integer function would be minus 4. Likewise, if I talk about the range of smallest integer function, then I'm referring to the values of y, which I'll be getting by putting some values of x as an input. So the range of y is equal to x would always be z. That's a set of integers. Because even though we substitute decimals or fractions, we will always, the value of y will always be an integer. Moving on to the properties of smallest integer function, though there are many properties, but predominantly we'll be studying about the two most important properties. If x is an integer itself, the smallest integer function remains as x without any change. Number 2 property says that the smallest integer function of x plus I, if I is an integer, equals to the smallest integer function of x plus I when added separately. We can understand this with the help of an example. If we take a number 7.6 and 2, 7.6 plus 2 gives us 9.6, and the smallest integer function of 9.6 is 10, which is equal to the smallest integer function of 7.6, that is 8. 8 plus 2 again gives us 10, which makes both the LHS and the RHS side equal and thus proves this property. Coming on to the applications of smallest integer function, then smallest integer function has different kind of applications in mathematical as well as other structural and analytical fields. It is used in base conversions and signal processing. Apart from it, it is also used in various kind of programming languages. Ceiling functions have a wide range of applications in Python programming, JavaScript, and other coding languages. If we have ever mailed a package, we will find out that the cost of those packages is actually a function of its weight. It is not exactly a decimal or a fractional number, but the smallest integer function or the ceiling function, which gives us about the cost of the package weight. Apart from it, if we have ever recharged our mobile phones and the data pack, the discounts and the offers which are given to us is in the form of a ceiling function, which is computed at the end of each and every network service pack provided to us. Apart from it, ceiling function is also used in duck typing, soft coding, JavaScript, and other coding languages. Ceiling functions also forms one of the most integral components of base conversions in Python and Excel. The base values of smallest integer function are used for computing out the significant results of various numbers, and hence it is rounded up to the nearest multiple of the ceiling function. Moving on, before winding up, let's get to know the difference between smallest integer function and greatest integer function. Ceiling function or smallest integer function is the least value of the integer that is greater than or equal to the specified number. But floor function or greatest integer function is the greatest value that is less than or equal to the specified number. In terms of notation, ceiling function is denoted in between small brackets or vertical brackets where the upper portion is being turned inwards. But if I talk about the notation of floor function, then it is denoted within big brackets or vertical brackets where the bottom portion is being turned inwards. We can also see a comparative graph analysis between smallest integer function and greatest integer function. With this, I wind up my presentation. Thank you.
Thank you, Anjali. You really did a commendable job today. Now I request the judges to ask the question, please.
Thank you, Anjali, for the nice presentation.
Thank you, sir.
You have done well. Mainly, you have collected many information regarding the application part, which is very, very essential.
Yes.
I hope all of your friends, those are in virtual mode, they have joined here. They have little knowledge about the application of this function. So I want to ask one question. You have said the smallest integer function, greatest integer function.
Yes, sir.
Suppose I will say that the function f of x is equal to square bracket x minus 1. This is greatest integer function.
Yes, sir.
What is the domain of this function?
So all real numbers. All real
All
numbers.
real.
Yes.
What
sir.
is the range of this
Even if
function?
So all integers. All integers will be forming the range of this function.
Okay, thank you. Very good.
Thank you, sir.
Good morning, all. Good morning, Amya
sir.
sir. Good morning, Amya sir.
Good morning, sir. Good morning, sir. Good morning, all.
Good morning, all the Department of Mathematics teachers. Let's start my video later. Sir, here, Anjali, you have nicely presented. I am very much
you, sir.
thankful to you.
Thank
But your presentation is a ceiling function. Am I right?
Yes, sir. Yes, sir.
Now, can you say the ceiling function is passing through origin?
Yes, sir. Because if we will take the number 0, then the ceiling function of 0 will remain as 0.
Okay. Do you have any idea about the symmetricity?
No, sir.
No. Okay. Actually, first quadrant, second quadrant, third quadrant, fourth quadrant, the graph is lies where? First, second, third, fourth.
So it lies between it lies in the first quadrant and it also lies in the third quadrant.
So from the graph, what do you understand?
So it resembles the appearance of a staircase. That is, if I'm taking two numbers, 2 and 3, and if you're taking any number which lies between 2 and 3, but it doesn't include 2, then there is a loop at the point 2.
No,
And
from the joke, I interrupt you, Anjali, but
Yes.
actually about the symmetricity. Symmetricity, you know, or you don't know? Symmetry,
No, sir. No idea about
circle, it has actually 4
Yes,
quadrants.
yeah, yes, sir. Then
Yes,
it divides
look.
it into equal halves. Yes, it talks about the
Okay, look.
orientation.
Looking into that symmetric property, so this actually function, your shilling function, is symmetric about what?
So I
First
couldn't get
quadrant.
it. Could you repeat it again?
Looking, okay, do you have symmetry property idea? Now I just
No,
tell
sir.
you the, okay, you don't have,
I know
okay.
the definition of symmetry, but apart from it, I don't know the symmetric
Okay.
properties of these series of
Okay,
functions.
suppose, how can say, apple you have, if you slice it, it will be 2 pieces. Once again, if you
Yes,
slice
sir.
it, it will be 4
Yes, sir. That I
pieces.
know.
So
Yeah.
you can say one quadrant is actually symmetric about other quadrant. Am I
Yes.
right?
Yes,
Similarly, your graph actually appear in the first quadrant and third quadrant. Tell me,
Yes.
it is symmetric about what?
So this is
It is
symmetric.
symmetric about what? Which
So
quadrant? It
in the
is
first
symmetric
and
about.
third quadrant, it is lying in the first and in the third quadrant.
Okay, nice, thank you. Actually, first quadrant, both symbols are plus, and the third quadrant, both symbols are minus.
Minus.
So,
Yes, sir.
so from there, what you find from there, it is symmetric about.
So I'm not getting your voice. Could you please repeat it once again?
First quadrant, both the symbols are plus. In
Yes, sir.
third quadrant, both the symbols are minus.
Minus. Yes, sir.
From this idea, what you understand, it is symmetric about.
So I'm not getting your voice. Your voice is breaking.
It is symmetric about.
So it is symmetric in the first quadrant and in the third quadrant. That's what I'm not getting your voice clearly.
Okay. Thank you very much, Anjali. Thank you.
Thank you, sir.
Thank you.
Thank you, Anjali, for your wonderful performance. I think it really gave a nice foresight to the viewers. So now let's move on to Anirudh Pradhan of class 12, section E. His topic is graphs of exponential functions. All the very best, Anirudh.
I hope I am visible.
Yes, you are visible, Anirudh.
And I also, like, my PPT is also visible, right?
Yes, your PPT is also visible.
Okay. So, a very good morning to one of your present over here, esteemed principal, revered judges, honorable supervisor ma'am, respected teachers, and my dear friends. This is Anirudh Pradhan of class 12, and today we will be exploring the graphs of the different functions. So the function I have chosen is the exponential function, and we can represent it using the formula y equals to f of x, that is equals to b to the power x, where b is greater than 0 but never equals to 1, and x is any real number. Let us take an example like f of x equals to 3 to the power x. Putting the value of x as 2, we are getting the value as 9. So coming to the properties of exponential function, the domain of exponential function is R, range is 0 to infinity, open at both the ends. So here you can see a graph of the exponential function. This is the standard graph of the exponential function. And what we can observe here, that it is continuous everywhere. We can't see any kind of breaking in between it. So therefore we can conclude it is continuous everywhere. Second, it is differentiable. We can't see any kind of corner-like structure in the graph. It is plain and simple. So that's, we can conclude that it is differentiable also. Then coming to the monotonicity, we can clearly see here that it is monotonically increasing. The concavity of the graph is not changing. So that's all about the properties. Now, I have differentiated it into 4 types, like making into the cases. In the first case, I have taken the function y equals to ab to the power x, where a is only a constant. And here a is greater than 0 and b is greater than 1. So graph will be looking like this, having an y-intercept at 0, a and forming an asymptote as x-axis. In the case 2, where a is greater than 0 and b is between 0 to 1, the graph looks something like this, forming an y-intercept at 0, a also, and forming an asymptote at x-axis. Now, the case 3 and case 4 are nothing but the complementary cases of case 1 and case 2, where the value of a is only changed to the negative and all the properties remain same here. Now, let me introduce to a new term known as Euler's number, which is also known as natural base E. Using this formula, we get the value of E as 2.71928, and it goes on like this. But our main focus is on the exponential function. So we can represent a Euler's number in the exponential form as y equals to e to the power x, where e is the Euler's number and x is the real number. Here is the standard graph of the function y equals to e to the power x. Here also I have divided into two more cases. This is nothing but it is the derivative of the first four cases that I have shown you earlier. Here only I have replaced in the function that I have shown earlier, y equals to ab to the power x. Here I have replaced b as e and a as 1. So the first function will be y f of x equals to e to the power x. The graph will be something like this, forming an intercept at 0, 1. Here I have taken another function like f of x equals to e to the power minus x. And the graph looks something like this, monotonically decreasing. And here also it forms the y-intercept at 0, 1. If we look at both the graphs in one scenario, we can observe that both the graphs meet each other, intersect each other at the point 0, 1, which is their y-intercept respectively. Now, coming to the applications of the exponential function. First application is the radioactive decaying. So let me first give an idea how it works. So just imagine I have taken a piece of uranium in my hand. Well, that's not possible in the reality, but let's imagine that. So with the passage of time, this piece of uranium in my hand will degrade, releasing a huge amount of energy. But the point to be noted here is the piece of uranium eventually gets smaller and smaller and smaller, but never disintegrates, never disappears completely. So the calculation of this part can be calculated using this formula, that is the number of active nuclei at the point time at the particular time t equals to number of active nuclei in the initial period of the experiment into e to the power minus lambda t, where lambda is a decay constant. Here you can see the graph of the radioactive decaying, like how the piece of any radioactive element is degrading with the passage of time. Now, coming to the another application of exponential function is the population count. So this is also similar to the previous one, where you can see in this graph, in the 12th century, population was below 1 billion. But with the passage of time, during 19th century, the population has increased up to 7 billion. And this can be calculated using this formula, that is population after a time t equals to population at the initial period of time into e to the power kt, where k is the growth constant. Now, this application is very interesting. Like we all have seen these kind of posters where initially one person was get infected during the COVID virus, then it infects two more people, then eventually they infect 4 more people, they infect 8, and this number goes on. Have you ever wondered how this number of cases have been calculated? Well, that's not a complicated case. It is calculated using exponential function. If we plot this number into the graph, you can see here is the graph of the number of cases in India during the initial phase of the COVID-19 breakout. So it looks like the exponential function, and it is an exponential function. So we can calculate it using the formula that I have shown in the previous one. Like we have also done some examples of it. So that's all in the exponential function. I hope you like it. Thank you for your patient hearing.
Thank you, Anirudh. Now I request our honorable judges to put some questions to Anirudh.
Thank you, Anirudh.
Thank you, sir.
Nice presentation. Really,
Thank
you
you,
have collected many information which are really helpful for us.
Thank
Only
you,
the
sir.
recent figure you have given, that is about the corona, how it is
Yes, sir.
exponentially growing. So you have said the exponential function is continuous everywhere.
Yes, sir.
Yes. And you also know what is the meaning of differentiability.
Yes.
Can
sir.
you tell me a function which is continuous everywhere but
Yes,
not
sir.
differentiable at 2 points?
Not differentiable at 2 point. It can be an example of modulus function, I guess, where we can say y equals to
Yes.
mod of x minus 2 or something like that. Or like, I'm not
So
sure directly, but it
you
is a
are
modulus function.
you are almost correct up to the thing. You said y is equal to modulus of x minus 1. Where this is
Yes,
not differentiable.
Sir, it is not differentiable at x equals to 1, and another point I'm not recalling
It is
right
not
now.
differentiable only at the breaking point. Okay.
Breaking point.
Thank you.
Thank you, sir.
Anirudh, am I audible here? Anirudh?
Yes, sir. Yes, sir. You're properly audible, sir.
Very good. You have actually presented very nicely about the growth
Thank you,
function.
sir. Thank you,
Now,
sir.
can you tell me about the decay function?
Yes, sir. Sir, it is like I have shown you the growth function, like it is monotonically increasing. The decay function is nothing. It is the monotonically decreasing part of the exponential function.
Now you have said that y is equal to e to the power x is a growth function.
Yes, sir.
Similarly, can you tell
Y-
me about the decreasing function or decay function?
So, for example, y equals to e to the power minus x.
E to the power minus x. Very good. Or inverse of e to the power x is how much? Inverse of e to the power.
Inverse of e to the power x. Is it the logarithm function?
Yes, very good. Now
Yes,
e
sir.
to the power x is a 1 onto function.
Yes, sir.
Is it bijective?
Yes, sir. It is bijective.
Where it is onto?
It is like in its domain, like 0 to infinity, open at both ends.
Okay, very good. E to the power x is less than 0. What is the value
Yes.
of x?
E to the power x less than 0.
0. What is the value of x?
X is 1. 1. Yeah, x is 1.
Are you sure?
Yes, sir.
You said
Yes, sir.
that your domain is 0 onwards infinity. How it
Yes,
is
sir.
possible that e to the power x is less than 0?
E to the power x is less than 0. It is not
Oh.
possible.
You said earlier it is possible and x value is equal to 1.
So what was your question? Like, can you repeat that? I thought it is e to the power x equals to 0, right?
E to the power x is less than 0. Is it
No,
possible?
less than 0. No, less than 0 is not possible.
Okay, very good, very good.
Yeah.
Thank you.
Thank you, sir. Thank you, sir.
Thank you, Anirudh. Thank you, judges. Next, we have Neera Banerjee of class 12E. All the very best, Neera.
Thank you, Nakshi. Is my video visible?
Yes, you are visible.
Is my okay? Is my screen visible now?
Yes, your screen is also visible. Yeah, your PPT is also visible.
Thank you. A very good morning to everyone. Esteemed principal ma'am, reverend judges, honorable supervisor ma'am, respected teachers, and my dear friends. Today, I, Neera Banerjee of 12E, am going to present my views on the topic graphs of different functions and on my chosen subtopic sine inverse and cos inverse. So first of all, I'd like to discuss that what is sine inverse and cos inverse exactly. We can say that sine inverse, or arc sine in short, is the inverse of the sine function, meaning that sine inverse of the ratio opposite side over hypotenuse will give the measure of the angle. Similarly, cos inverse of the ratio base upon hypotenuse will give the measure of the angle. Hence, in short, we can say that sine theta is equal to x, which will imply that sine inverse of x will be equal to theta. Similarly, cos theta is equal to x, which will imply that cos inverse of x will be equal to theta. Here we can see the graphs, and we will discuss the domain and range of the graph shortly. So, domain and range of sine inverse of x and cos inverse of x. Before we discuss that, I would like to ask that since we know that we know the domain and range of sine and cos, I think we can say that if we interchange that we'll get the sine domain and range of sine inverse and cos inverse. But that's not entirely true, because we can't do that. To make sure that we find the inverse of a function, we need to make sure that it's bijective. And to make sure that it's bijective, we need to take certain branches from the sine and the cos graph. Hence, we can say that the domain of sine inverse and cos inverse are same, that is -1 to 1 close bracket, but the range of sine inverse is -π/2 to π/2, and the range of cos inverse is 0 to pi. And we can also say that sine inverse is positive in the first quadrant and negative in the fourth quadrant, and cos inverse is positive in the first quadrant and negative in the second quadrant according to the ASTC rule. Now we'll move on to the graph and properties of sine inverse of x and cos inverse of x. Since we have already discussed the graph, I'd like to discuss the properties. Sine inverse of x is equal to x for every x in the interval -1 to 1, close bracket. Sine inverse of minus x is equal to minus sine inverse of x. Cos inverse of minus x is equal to pi minus cos inverse of x. Cos inverse of x is equal to x for every x in the interval -1 to 1, close bracket, and sine inverse of x plus cos inverse of x is equal to pi/2. I'd like to discuss two properties in detail with their graphs, that is sine inverse of sine x is equal to x for every x in the interval -π/2 to pi/2. Hence the graph would look something like y is equal to x. But what if x lies between pi/2 to 3π/2 or 3π/2 to 5π/2? Hence we have to adjust the angle accordingly. So let's say for pi/2 to 3π/2 it would look something like y is equal to pi minus x, and hence we can draw the graph for all the intervals. And we can say that the nature of the function is odd, and the domain is R, and the range lies from -π/2 to pi/2. And for cos inverse of cos x is equal to x for every x in the interval 0 to pi, close bracket, we can say that y is equal to x is from 0 to pi. What if we say from pi to 2 pi? The graph would look something like y is equal to 2 pi minus x. And we can say the nature of the function is even, and the domain is R, and the range lies from 0 to pi, close bracket. Now I'd like to discuss some of the practical uses of sine inverse of x and cos inverse of x. First we have house plans, then scale models and other uses, aviation, and the Leaning Tower of Pisa. We'll discuss them in detail. First of all is house plans. Sine inverse of x and cos inverse of x can be used to find the optimal angle for the optimal sunlight, so that we can have adequate heating and cooling during summer and winter respectively. It can be used for perfect window placement, and it can be used for building houses. And next, scale models and other uses. It can be used to scale models of bridges for 3D printing, and it can also be used for building escalators. It can also be used to know the angle at which the anchor should be thrown, and it can also be used for simple daily things like how to place the ladder, at which angle should we place it. For aviation, it is a very important part of aviation, because during updrafts and downdrafts, it helps the airplane to find the perfect glide angle to correct the flight path so as not to crash it. It can be used for takeoff and landing of the plane, and it can also be used for finding the angle of attack for fighter jets. And lastly, the Leaning Tower of Pisa is the prime example of the use of sine inverse of x. The Leaning Tower of Pisa was said to have toppled over at 5.4 degrees, but it was leaning at 5.5 degrees and it was still continuing to lean. So to preserve that monument, the engineers found a solution. They dug below the Leaning Tower of Pisa so that the tower would sink into the cavity, and they placed steel cables to anchor the tower so that it would still preserve that tilt and it would not topple over. That's the end of my presentation. Thank you.
Thank you, Neera. That was really awesome. I request the judges to ask their questions, please.
Neera, you have done
Yes, sir.
nicely explain the sine inverse and cos inverse and its application. I'm very much happy.
Thank you, sir.
But in
Thank you,
between,
sir.
you have said the periodicity, the term you have been used. Am I right? Periodicity.
Sir, yes, sir.
What
Yes,
exactly that? Can you explain with respect to other function how we came to know the periodicity?
Sir, periodicity is basically when the graph is basically repeating itself we can say that it's periodic. The periodic graph has a periodicity, and there's a interval of periodicity. For example, that graph that I was talking about, sine inverse of sine x, it is repeating itself after 2 pi. So we can say that the periodicity is 2 pi. It is periodic after the interval of 2 pi.
Okay. Sine x plus 2 pi is how much? Sine x plus 2 pi. Sine x
So-
plus 2 pi is how much? Tell me.
So 2 pi plus x. So sine x.
X plus 2 pi. Sine of x plus 2 pi is how much?
So is it sine x?
Yes. Sine of x plus 2 pi is sine x. Sine of x plus 4 pi is how much?
So sine x.
Now, can you say 2 pi is the period of sine and 4 pi also period of sine?
Sir, 4 pi is a multiple of 2 pi, no? So periodicity is
No.
2 pi only.
2 pi. Very good. Very good. Now, sine inverse x is the same as cos inverse x. For what value? For what value
So
of
for
x?
so for sir, pi by 4.
Is it possible? Is it possible?
So sine and cos are equal at pi by 4.
Now you are talking about sine inverse and cos inverse.
So yes, inverse will also be equal, no?
Inverse
Sine
also
inverse
equal.
of pi by 4 will be equal to 1, and cos inverse of pi by 4 will also be equal to 1. So the values will be equal.
Sine inverse of pi by 4 is equal to 1. Are you sure?
Yes, sir.
Okay, you are a bit confused. Okay, anyhow, nicely presented and explained very nicely sine and cos. Very good. Over to
Thank you,
Amir
sir.
sir.
Thank you, Nira.
Thank you, sir.
Can you say what is the principal principal branch of sine inverse x?
So principal value branch is minus pi by 2 to pi by 2 closed interval.
Can you say any other branch in which sine inverse x is defined?
So it can also be defined at pi by 2 to 3 pi by 2 closed interval, or 3 pi by 2 to 5 pi by 2 closed interval, or minus 3 pi by 2 to minus pi by 2 closed
Very
interval,
good.
etc.
So can you say why we cannot take from 0 to pi closed interval?
So because then that would not be bijective. The function would not remain bijective, so it is impossible to find the inverse only.
Not bijective means what? What do you
So
mean
not
by
bijective means it is not 1 1 and on 2.
What is 1 1 graphically? Can you say?
Sir, 1 1 is when um, sir, 1 1 is when the codomain is equal to the range.
Codomain equal to range. I think you know the thing, but you are confusing.
Yes,
That
sir.
is
Yes, sir.
on 2.
Yes, sir. Yes, sir. There
Okay.
is.
1 1. You just think about the term 1 1. From graph,
Yes, sir. 1 1. Yes, sir.
graph, how will you confuse? Just
Sir,
look
from
at the graph.
graph. Sir, when the graph will be a straight line.
Graph will be a straight line. Suppose you have the graph of sine x or sine inverse x.
Yes, sir.
I will say it is 1 1 or not.
Yes, sir. So when we look at the graph, we can see that it is repeating after a while.
Okay.
So
Very good.
1 unit will take.
Thank you.
Yes, sir. Thank you, sir.
Thank you, Neera. Thank you, judges. Neera, the time you put in really shows. Good job. Now, I would like to call Rohit Mishra of class 11A to present his opinion on his topic.
Am I visible?
Yes, you are visible, Rohit.
Is my presentation visible?
Yes,
Hello?
your presentation is visible.
Yes, thank you. Good afternoon to one and all present here. Esteemed Principal Ma'am, revered judges, Honorable Supervisor Ma'am, respected teachers, and all my dear friends. Today I, Rohit Kumar Mishra of class 11A, am going to speak about the given topic, modulus function and signum function, the graphs of modulus function and signum function. The contents that are going to be displayed in this slide of mine are modulus function and signum function, the definition, domain and range, graph, and numericals of both. Now comes the modulus function. How can we define the modulus function? The modulus function can be defined as a function f such that f of x is equal to mod x. Here, x is any real number. Therefore, for all real numbers, f of x will be equal to x if x is greater than 0. F of x will be 0 if x is equal to 0, and f of x will be minus x if x is less than 0. It is minus x here because if x is less than 0, it is a negative number, and minus of any negative number will give a positive number of the same magnitude, which is the modulus function. Therefore, now we can conclude that the domain of the modulus function is nothing but the set of all real numbers R, while the range of modulus function is the set of all non-negative numbers. The graph of modulus function is something like this. It is V-shaped and it is present only in the first and second quadrant, as the modulus function of both positive and negative numbers is always positive. Therefore, the modulus function is always V-shaped and present in the first and second quadrant. Let us discuss a numerical related to the modulus function. Y is equal to f of x, which is equal to modulus of x minus 1 plus modulus of x minus 3. Find the range and draw its graph. The given information is y is equal to f of x, which is equal to mod x minus 1 plus x minus 3. Therefore, here the critical points are x is equal to 1 and x is equal to 3. Now, what do I mean by critical points? Critical points are the points where the modulus function gives us the result 0. Here, if x is equal to 1, x minus 1 will be 0. Modulus of x minus 1 will also be 0. If x is equal to 3, then x minus 3 will be 0. Therefore, modulus of x minus 3 is also 0. Therefore, y will be equal to f of x, which is equal to minus x minus 1 minus x minus 3 if x is less than equal to 1. Because in this case, the number is less than both 1 and 3. And so we'll get a negative number in both the cases. So we have to multiply minus 1 in both the cases. We get the resultant as 4 minus 2x if x is less than equal to 1. Now, if x ranges from 1 to 3, we get x minus 1 minus x minus 3. This is because the numbers between 1 and 3 are greater than 1, and a greater number subtracted by a smaller number is always a positive. Between 1 to 3 are less than 3. Therefore, the subtraction of x minus 3 will be negative. To convert it to positive, we have to multiply a minus 1. Here we get the resultant of 2. Therefore, y will be equal to 2 if x ranges from 1 to 3. And if x is greater than equal to 3, both the cases will be positive. So we don't need to multiply minus 1 in any of them. So we get x minus 1 plus x minus 3, which is 2x minus 4. From the given question, this is the graph. We have got that the minimum value of y will be 2 when it ranges from 1 to 3. And before 1, it is 4 minus 2x. And after 3, it is y is equal to 2x minus 4. Therefore, the range of this function is from 2 to infinity. It is close bracket 2 to infinity. And the domain of a modulus function is always the set of all real numbers. Next, let us move to the Signum function. The Signum function can also be defined as a function f such that SGN of x, Signum function can also be denoted by SGN, is equal to f of x, which is equal to mod x by x for x not equal to 0. Because if x will be equal to 0, then we'll get a non-real number. Here x is any real number. Therefore, now we can conclude that domain of Signum function
Anirudh, you're not
is
audible.
equal to the set of all real numbers, while the range of Signum function is equal to 0. It is -3 less than 0, and it is 1 when x is more than 0. Am I audible?
Yes, now you're audible, Anirudh.
So this is how we can define the Signum function. The domain of Signum function will be the set of all real numbers, while the range of Signum function will be -1, 0, or 1. This is the graph of Signum function. It is not 1 when x is 0 because x is not equal to 0. So it is all numbers greater than 0 have 1, all numbers less than 0 have -1 as f of x. Some special numericals related to the modulus function are something like this. Redefine the function y is equal to f of x, which is equal to a modulus of x minus 2 by x minus 2. Find its domain, range, and draw its graph. The given information is y is equal to f of x, which is equal to modulus of x minus 2 by x minus 2. Now we know that for y to be real, the denominator must not be equal to 0. So x minus 2 should not be equal to 0. Therefore, x should not be equal to 2. Therefore, the domain of this function is all real numbers except the set containing 2, and the range is -1 or 1. And this is the graph of this function. Next, let us move to the last numerical of my presentation. Redefine the function f of n, which is equal to x modulus of x plus 3 by x plus 3. Let y is equal to x plus modulus of x plus 3 by x plus 3. And for y to be a real number, its denominator must not be equal to 0. Therefore, x plus 3 must not be equal to 0. Therefore, x must not be equal to -3. Therefore, the domain of the function should be the set of all real numbers except the set containing -3, and the range should be 1 and -1. And this is the graph of the function. Thank you.
Thank you, Rohit. You did a really commendable job. The judges are requested to put forward their queries, please.
Thank you, Rohit.
Thank you, sir.
So you have given the presentation on modulus function and signum function. I have a question on your
Yes,
modulus
sir.
function. Suppose I will say f of x is equal to -x by modulus of x. Can you say what is the domain and range of this function?
Sir, f of x is equal to -x by modulus of x.
Yes.
Sir, if f of x is equal to -x by modulus of x, the modulus is always positive and it is x is -x. So it is either -1 or 1. The range is -1 or 1. And x should not be equal to 0.
Why not equal to 0?
Because, sir, if it is equal to 0, then the denominator will become 0. And if the denominator becomes 0, then it is not a real number.
Okay. Thank you. Sai sir, please.
Thank you, sir.
Rohit, you have done very comfortably about mod x and signum function. Now you have actually used the word range. Range alternatively, what we understand alternatively. Range
Sir, I
means
couldn't
what?
hear you clearly.
Range means what? Alternatively, what we are getting from the range. If a graph is there, what
Sir,
what you are
yes,
getting
sir.
from? Yes. Tell me.
Sir, range is in graph. Range is depicted in the y-axis and the domain is depicted in the x-axis.
Okay, very good.
And
very
range
good.
is the result of a function.
Very good.
The possible
But
results of a function.
Mine is where if a graph is given to you,
Yes, sir.
suppose you are able to draw the graph, can you find about maximum value and minimum value?
Yes, sir. If we take the example of modulus function, in one of the examples that I showed, the minimum value was 2. When and the maximum value is not fixed, it is infinitive. So
Okay.
minimum value is fixed and maximum value is not fixed.
Okay, can you correlate with your domain and range about max and mean values?
Sir, if y is minimum, then range is also minimum, and the maximum range is infinity. The minimum range is 2.
Okay, very good. See, I'm just trying to ask the question. Maximum value is given to you, minimum value is given to you, function is given to you. Suppose you are going to find the range. What you are going to do?
So range will be equal to close bracket minimum value, comma close bracket maximum value.
Very good, very good, very good. And mod x you have done, mod x is symmetric about what?
About y-axis?
How you came to know?
Sir, because the y-axis divides the graph into 2 equal parts.
Okay, suppose a human being is there, I'm trying to bisect longitudinally. Now, what about your answer? It is symmetric about?
Sir, a human being is bilaterally symmetrical.
Okay, very good, very good. And x square root over is equal to how much?
X.
X square root over is equal to how much?
X.
Very good, very good.
Thank you, sir.
Now next one.
Thank you, Rohit. Thank you,
Thank you.
judges. Rohit, I'm really curious about your secret for this splendid output. Now, I would like to call upon Preeti Parnarath of class 11G.
So am I audible?
Yes, you're audible.
Screen is visible.
Screen is visible.
Good morning to one and all present over here. Esteemed Principal Ma'am, revered judges, Honorable Supervisor Ma'am, respected teachers and my dear friends. Today I am going to present about graphs of different trigonometric function, under which I will be discussing about the sine function. Under the sine function, we will be discussing about the sine x, sine square x, sine 2x, sine 3x, sine x by 2, sine mod x, mod sine x square, sine x by 3, and root sine x functions. Now, for all these functions except the root sine x function, the domain is same. That is, it is defined for all real values of x. So, sine x function. Its range is closed interval -1 to 1. This is the graph of the sine x function. As you can see, the graph repeats itself after every pi interval. The highest point of this graph is 1 and the lowest point is -1. Hence, the maximum value of sine x is 1, whereas the minimum value of sine x is -1. Sine square x function. Its range is closed interval 0 to 1. This graph is a continuous graph. As the square of a negative number is always positive, y has no negative value in this graph. This graph is also symmetric to the y-axis. That is, the y-axis divides the graph into 2 equal parts. Sine 2x functions. Its range is closed interval -1 to 1. This graph repeats itself after every pi by 2 interval. The highest point of this graph is 1, whereas the lowest point is -1. Sine 3x function. Its range is also closed interval -1 to 1. This graph repeats itself after every pi by 3 interval. The highest point of this graph is 1 and the lowest point is -1. Hence, its range is closed interval -1 to 1. Comparison between sine x and 3x graphs. The red line represents sine x, whereas the blue line represents sine 2x function and the green line represents sine 3x function. The sine x graph repeats itself after every pi interval. Whereas the sine 2x graph repeats itself after every pi by 2 interval. The sine, on the other hand, the sine 3x function repeats itself after every pi by 3 interval. Sine x by 2. Its range is closed interval -1 to 1. This is the graph of the sine x by 2 function. This is a continuous graph. Sine modulus x. Its range is -1 to 1. This graph is also symmetric to the y-axis. We can see that both the positive side and the negative side of the graph originate at the origin. Modulus of sine x. The modulus of a negative number is always positive. Hence, its range is closed interval 0 to 1. As the modulus of a negative number is positive, y has no negative value in this graph. This graph is also symmetric to the y-axis, as the y-axis divides both sides of the graph equally. Sine x square function. Its range is closed interval -1 to 1. This graph is also symmetric to the y-axis. This graph is a continuous graph. Sine x by 3 function. Its range is also closed interval -1 to 1, and its graph is a continuous graph. Root over of sine x. Its domain is set of x such that x belongs to R, and sine x belongs to 0, closed interval 0 to 1. Its range is a closed interval 0 to 1. This graph is a discontinuous graph as the curves are not linked together. Application of the sine wave. Application in financial modeling and economic data. The sine function and sine waves are widely used to model economic and financial data that exhibit cyclic or periodic behavior. The variable in such modeling exercises is time. For example, a business selling consumer discretionary goods is likely to experience strong seasonality in its sales and revenues. Consumers tend to spend more money in the lead up to the holidays and less money immediately after the holidays. The sine wave helps us to make the graph of this situation. Application in art integration. The sine waves are used for creating different patterns in sarees, rangoli, shawls, 3D graphs, etc. With this, I conclude my presentation. Thank you and have a nice day ahead.
Thank you, Pritiparna. Over to the judges to ask the questions.
Thank you, Pritiparna, for the energetic presentation. Really,
You're welcome,
you
sir.
have collected good knowledge on this. So, can you say what is the maximum and minimum value of sine x?
Yes, sir. It's 1. Maximum is 1 and minimum is -1.
Very good. So now my question is sine x into cos x.
Yes, sir.
Sine x into cos x. What is
Yes,
the
sir.
maximum and what is the minimum value?
So maximum value is 1 and minimum value is also 1 because -1 into -1 gives 1.
So sine x maximum value is 1, minimum is
Sorry. Maximum value is 1 and minimum value is 0.
Sine x into cos x.
Yes, sir. So 1 and 0, closed interval 0 to 1.
You should multiply 2 and divided 2 so that it will be 2 sine x into cos x.
Okay.
And what is 2 sine x cos x? What is 2 sine theta cos theta?
So 2 sine theta cos theta is
Yes.
equal to sine 2 theta.
Sine 2 theta. So now this is in terms of sine x.
Yes,
you
sir.
can say what is the maximum and minimum. And with
Yes,
that
sir.
also you have another factor. So considering all these things, you have your answer. So thank you. Over to Sai sir.
Priti,
Yes, sir.
you have actually presented very nicely.
Thank you, sir.
Now you have been used the word like periodicity, periodic, isn't it? Sin x is a periodic function.
Yes, sir. It repeats itself after every pi interval.
Pi? Are you sure?
Yes, sir. Yes, sir.
Okay. What about cos x periodicity?
So it also repeats itself after pi interval.
Pi. Okay. Now you show your slide, the first slide about sin x. First slide.
Yes, sir. I have to share the screen.
Yes.
Yes, sir. Here.
Let's see where it actually repeated. You find yourself.
So pi. Here.
How it will be by completing one graph, na? See, it is 0, sine 0, 0, sine
Yes, sir.
91. After one complete graph, then after 1 second, it will repeat the same thing, isn't it?
Yes, sir.
So pi plus pi, that is 2 pi.
Yes, sir.
Understood?
Yes, sir.
You are bit nervous? No, na?
No, sir.
No, na? Okay, very good. So sin x is periodic about 2 pi. Huh? What
Okay, sir.
about, okay. Now sin x maximum value is 1. Sin x minimum value is -1.
Yes,
Now
sir.
what about sin square x minimum value?
So sine square x minimum value is 0.
Very good. Maximum value?
1.
Very good, very good. Yeah, sin x maximum 1, cos x maximum value is 1. Once again, I will repeat the same question as like your sir what actually asked. Sin x into cos x. What about the maximum value?
So 1 and -1, as sir explained, that will come as if I multiply 2 and divide by 2, it's coming sine 2 theta formula is coming, so that will be 1 and -1.
Okay, very good. Just write in your paper one thing, sin x into cos x. Do you have paper? Do
Yes,
you
sir.
have? Write it. Sin x into cos x. Multiply 2, divide 2. Numerator is sin 2x. Again half into sin 2x. Now half into max value of sin 2x, that is 1. Half into 1. How much? You are muted. Just actually unmute
Yes, sir.
yourself. You are okay.
Half into 1 is half.
I know.
1 by 2.
Sir actually said the same thing. Understood?
Yes, sir.
Okay.
Yes.
Now it is a very
1 by
important
2.
question. Okay, 1 by 2.
I
What
guess.
is the minimum value? You tell me. Minimum value.
So -1 by 2.
Very good. Very good. Okay. Thank you very much.
Thank you, Preeti Parna. Indeed, a remarkable performance by your side. Now, I would like to call Deepti Abhishekta of class 12E to start with her presentation.
Am I audible?
Yes, you're audible, Deepti.
Is my presentation visible?
Yes, your presentation is visible.
Math is not about numbers and equation. It is just about understanding. A very warm afternoon to one and all present over here. Esteemed Principal Madam, Revered Judges, Honorable Supervisor Madam, respected teachers, and my dear friends. Today I, Dipti, is going to present on graphs of different functions on tan inverse x and cot inverse x. Before moving on detailed about tan inverse x and cot inverse x, we will be knowing the tan x and cot x domain and range. The domain of tan x is x belonging to R and x is not equal to 2n plus 1 into pi by 2, where n is integers and the range is all real numbers. For cot x, the domain is x belongs to R and x is not equal to n pi and n belongs to integers and the range is all real numbers. Now, some of the basic properties of inverse trigonometric functions, like inverse trigonometric functions are many one functions. If we restrict the domain of these functions, they become bisective, that is 1, 1 and onto. Since I'm focusing on tan inverse x and cot inverse x, so I will be discussing about domain and range of tan inverse x and cot inverse x. So tan inverse x domain is all real numbers and the range is minus pi by 2 to pi by 2 open interval, and for cot inverse x domain is all real numbers and the range is 0 to pi open interval. Now let's see the graph. This is why if you are taking y equal to tan x for interval, as x will be your domain, so it will be plotted in x-axis and y will be your y-axis. But it inverse, it will be x will be plotted in y-axis and y will be plotted in x-axis. Here is the graph. At minus pi by 2, it is minus infinity, so dotted lines are present, and pi by 2, it is infinity. So here again the dotted lines are present. So we will be plotting these 3 points, like minus pi by 4 minus 1 at origin, and then pi by 4 at 1. Here we will be taking the point. So by joining this point, we will get a curve, and that is where your y equal to tan inverse of x. Now you can see this tan inverse of x is symmetric about x-axis, and tan inverse x is also an increasing function. Maximum and minimum value is not defined for tan inverse x, and tan inverse x is a periodic function. Something more on tan inverse, if you are taking y equal to tan x and x equal to tan inverse y, your y will be belonging to all real numbers, and obviously your x will be belonging to minus pi by 2 to pi by 2 open interval. Now if you are taking tan of tan inverse x, that gives you x. For x belonging to all real numbers will coming around as a straight line graph where y equal to x. Now, if you are considering tan inverse of tan x equal to x for all x belonging to minus pi by 2 to pi by 2 open interval, and if you see the graphs will be like a slanting portions in at origin or pi. If some other points, if you take this like this, lines will be coming. The other branches of tan inverse x will be like 3 pi by 2 to 5 pi by 2 open interval, minus 3 pi by 2 to minus pi by 2 open interval, pi by 2 to 3 pi by 2 open interval. Here comes your cot inverse x. For any value of cot inverse x is the angle measured in the interval 0 to pi open, and that is the value of cot x. So cot inverse cot x equal to x for any interval like from 0 to pi open interval, and for cot of cot inverse x will be x for any value of x, that is real numbers. Now here is the graph. If you are taking y equal to cot x, and here as for the points, and y equal to cot inverse x, the domain will be all real numbers and range will be 0 to pi open interval as we have seen before. So here x it is 0, and for y it is infinity, and for pi it is also infinity, and pi by 2 it is 0. So these points will be plotted in y-axis and this y will be plotted in x-axis. So here we will be seeing that at 0 it is infinity and pi it is infinity. Something different, the graph will look like this. At pi the dotted lines are already being present, and at pi by 2 it's 0. So we will be pointing the point over here, and you will be putting a curve just like the graph will be decreasing. So cot inverse x is a decreasing function in its domain. So we have discussed the main principal value branch of the cot inverse x. So other branches are like pi to 2 pi open interval, 2 pi to 3 pi open interval. So cot of cot inverse x where x belongs to R, and cot inverse cot x where x belongs to 0 to pi open interval. This is a graph of cot inverse cot x. The maximum and minimum value of the cot inverse x is also not defined, and cot inverse x is also a periodic function. Now let's move on to the application part. Now, since the Leaning Tower of Pisa, for that, the angle of tiltation is also calculated with the help of inverse trigonometry. Now, for carpentry, the tan inverse x and cot inverse x functions is basically being used. It is a pyramidal structure. You can see the carpentry for that tan inverse and cot inverse x is used, so that you can make sure that the material that is being used that fix the space that is available. Now let's have a short activity. For example, you are mapping out with a hiking trip to a new spot on a map. You want to go with a course hovering 2.5 miles east and 3 miles south. Let's suppose that you started from here and you have finished over here. Now you want to know that how much sorted distance I have traveled. For that, you have to know the measure of the angle. Now for that, you have taken tan theta. Now tan theta is base upon perpendicular, that is 3 upon 2.5. Now taking tan inverse on both the sides, you get tan inverse tan theta equal to tan inverse of 3 upon 2.5. So your angle will be coming around as theta equal to 50.2 degrees. So at 50.2 degrees, you can know that yes, at this angle, I will be tilting to reach my finish point. Is this so interesting? So applications of inverse trigonometry and using tan inverse x and cot inverse x makes your life so easy that you can, wherever you go, and use this function in a very proficient manner. With this, I come to the end of my slide. Thank you and have a great day ahead.
Thank you, Dipti. Now I request the judges to ask their questions, please.
Abhishekta,
Yes, sir.
you have presented very nicely about tan inverse and cot inverse and its application. Okay, thank you for that. Tell me, tan inverse x is a bijective function.
Yes, sir.
Again, you have told that that is an increasing function.
Yes, sir. As a graph, it was increasing function, and we can see
Okay.
there's a symmetric about x-axis also.
Very good. Now, increasing functions are 1, 1. Is it true or false?
Yes, sir, it is true.
Decreasing functions are 1, 1. Is it true or false?
Yes, sir, it is true.
Okay. Now, tan inverse x, what you are getting in the output? Is it an angle or it is a tangent or what you are getting? Tan inverse x.
We will be getting an angle. If we will take the derivative, then we will get the tangent.
Okay, very good, very good. Now, tan inverse x is equal to 1. What values you are getting?
At tan inverse x equal to 1 means we will be getting as an angle pi by 4.
Pi by 4. X is equal to pi by 4.
4.
Any more values are you getting?
So 5 pi by 4.
Why it is so?
Sir, because it is the multiples of that, that's why, or multiples of pi, that's pi by 2.
That means tan inverse x is a periodic function or not?
Yes, sir, it is a periodic function. It is an odd
Okay.
periodic function.
What about its periodicity?
Sir, it is its periodicity is pi.
Are you sure? Okay, you have a nice culture. I am very much appreciate about you. Please have a glance about 1 second. Okay, thank you.
Sir, yes.
Next to Amir sir. Sir, please.
Thank you, Dipti.
Thank you,
It's a
sir.
nice presentation. So can you say the slope of a line in terms of tan? Very simple question I am asking.
Sir, that will be y2 minus y1 upon x2 minus x1 if you are taking the points.
That is the slope of a line if 2 points are given.
Yes, sir.
So in terms of tan, can you say?
Sir, that will be
You know the answer.
so that will be tan x plus tan y upon 1 minus.
Can you say what is angle of inclination? The first class of coordinate geometry you have learned in class 11.
Sir, angle of inclination, the
angle made by the line with the positive direction of x-axis in anti-clockwise manner.
Yes.
That angle, if theta, then tan theta will be the slope of the line.
Yes.
So whatever application you said or you will culture on that, definitely there is a use of this. There is a vast use of this, the slope of line. Thank you
Thank you, sir.
for the nice presentation.
Thank you, Dipti. Thank you, judges. Amazing effort by Dipti. Now let us move on to the next participant, that is Bidhu Bhushan Patra of class 11, section E.
Am I visible?
Yes, you are visible.
Is my screen visible?
Yes, your screen is visible too.
Okay. So good afternoon, everyone. Esteemed principal ma'am, honorable judges, respected supervisors, and all my dear friends. So today in this mathematics seminar, our main topic is about graphs of different functions, and I have chosen the subtopic as greatest integer function and fractional part function. So let us begin. That is, functions, or which is known as elect, is broadly classified into algebraic functions and transcendental functions. Now, algebraic function is further divided into polynomial function, rational function, irrational, then piecewise. And under transcendental function, there is logarithm, inverse trigonometric, exponential. Similarly, under piecewise, which is again divided into modulus function, greatest and least integer function, fractional part function, signum function, and defined function. So let us begin. That is the first one, that is greatest integer function. So the greatest integer function, it is represented by x within square brackets for any real number. So what is this function? It is the function which rounds up the real number down to the integer less than the number. So here is the graph. Yeah, let me show the pointer. In this graph, which is already labeled, here we can see some dark circles are there and some light circles. These circles, the light circles, do not include that number. That is, the integer is not included, while the dark circle includes that number. So the function rounds up the real number down to the integer less than the number. So if a number is taken and if it has been asked to find the greatest integer function, then we have to take the integer which is less than the number. Now, as in the figure, we can see it is arranged by steps or in the form of staircases. So it is a type of step function. And from this graph, we can see that the domain is on the x-axis, which is going to infinity towards both the sides of the x-axis. So domain x belongs to R, that is real number set. Similarly, range is range only includes the integer set, that is y belongs to z. Now comes to some properties and examples of greatest integer function. So first one is if x is an integer, then greatest integer function of x will be x. Now second one, if and only if at least either of x or y, means that from both the x or y, either one of them is an integer, then greatest integer function of x plus y will be equal to greatest integer function of x plus greatest integer function of y. Similarly, third point, if x is an integer, then greatest integer function of x and its opposite, when they both are added, they will be give 0 as the sum. And similarly, the fourth point, if x does not belong to integer, then the greatest integer function and its negative addition will give -1. Here, to make it simpler, one example is given, that is 6.1 greatest integer function plus negative of 6.1 greatest integer function, which is giving 6 plus -7, because -6.1, if we take the greatest integer function, then it will give -7. So it is coming -1. So here in this table, we can see some more examples are given. By using these properties, we can easily solve this. Now comes to a numerical, that is given, find the value of x such that greatest integer function of x plus 3 is equal to 3. Now from the definition and the properties we have read, we have 3 less than equal to x plus 1 less than 4. So by subtracting in this inequality, we get x which is between 2 less than equal to x less than 3. So x will be closed interval 2 and 3 open interval. Let's come to our second topic, that is fractional part function. So fractional part function is represented by x within curly brackets for any real number. So the main thing is about this is that it is the difference between x and if fractional part function of x is taken, then it will be equal to x minus greatest in the function of x. So in the graph here, we can see it is already labeled. And from this graph, we can find out the domain as R, because here it extends towards opposite to infinity towards opposite sides of the x-axis, and range we can see that 0 is within dark circle and 1 is within light circle. So 0 will be within closed interval and 1 will be open interval. So range will be 0 to 1, 0 closed interval and 1 open interval. So for non-negative real numbers, the fractional part is just the part of the number after the decimal. So here one example is given: 3.64 fractional part function will be equal to as we have seen in here in the property. So it will give 0.64. And here one note is that fractional part function can never be non-negative. Sorry, can never be negative. It is always a non-negative. Now comes to some properties and examples. So first point, if x belongs to z, that is integers, then 0 less than equal to fractional part function of x less than 1, and 0 will be equal to fractional part function of x. Now second one, that is fractional part function of x, if it is added to fractional part function of minus x, it will give 0 if x belongs to integer, but it will give 1 if x does not belong to integer. Now third point, if a and b belongs to integer and if b is greater than 0, then the division of a by b and the fractional part function will be equal to r by b, where r is the remainder from dividing a by b. So here is an example given: 9 plus minus 9, both having fractional part function, will give 0. But here secondly we can take 9.01, which is not an integer, and here also minus 9.01, it is also not an integer. It will give 1. Why? Because here we get 9.01, by solving its fractional part function we get as 0.01, and by solving this we get 0.99. So by adding this we get 1. So here it is again repeated, that is fractional part is always non-negative. So here are some more examples by solving. Here let us see this one, that is fractional part function of pi. So pi minus 3, that is we have taken fractional part function of x, that is x minus greatest integer function of x. So here pi, where is 3 come? So value of pi is 3.14. So greatest integer function of 3.14 is 3. So pi minus 3 is around simply taken as 0.14159. So in this way examples can be solved. Now one numerical, that is let x be a positive real number such that x square plus fractional part function of x whole square minus 27, sorry, equal to 27. So find the value of x. So here we can get a quadratic equation, and by solving the quadratic equation using the quadratic formula, we get the value of r, that is minus 5 plus root over 29 whole divided by 2. Similarly, by putting the value of r in the equation of x, we get the value of x as 5 plus root 29 whole divided by 2. So here comes some applications, that is at the first, that is shipping cost. It is an application of greatest integer function. We have seen in various shipping companies or in Amazon, or on their delivery charge in Amazon, Flipkart, or postal charges in the post office. Their postal charges or shipping charges are given according to their weight. So here 1 gram up to 2 gram, excluding 2 gram. 2 gram is not included. So it will cost 1 rupees here in the table given. Similarly, up to 7 gram, up to 8 gram, excluding 8 gram will give 7 rupees. Some more applications, that is digital signal processing. Here some graphs of the digital signal processing is there. Microphone, how the waves are going, and examination grades, that is the grades are which we get in examination after getting marks. So income tax slab, goods and services tax slab, their graphs, they resemble the greatest integer function. Similarly, postal packaging grade, it is also there. So that was all about my topic. So thank you for patiently hearing.
Thank you, Bidhu. Now I request the judges to ask their queries.
Vidhubhushan.
Yes, sir.
Okay, very nicely presented the integer function, fractional function in its application, day-to-day life application. Again, about the economics, about the GST, about the postal, everything you have covered. You have given a much time on that. I'm really appreciate. But okay. Now I have a question about the modulus function. Do you have one command on that? Do you have command on that? Yes.
Okay,
So mod x is equal to root over of x square. Is it true or false?
yes, sir, it is true.
The root over of x square is equal to x. Is it true or false?
Sir, it is false.
Why it is false?
Sir, because root over x square, it can be plus x or minus x.
Okay, that's why it is a mod x. Am I right?
Yes, sir.
Okay. Now, do you have a command on domain and range? Tell me.
Yes, sir.
Okay. 1 upon x. What about the range? 1 upon x.
Sir, range will be r minus 0.
Very good. Now 1 upon x minus bracket x.
Sir, who is bracket?
Bracket x, you have told now that bracket x means greatest integer function.
Yes, sir.
1 minus bracket x, it is understood that greatest integer function. Okay.
Sir, it will be 0 open to 1 closed. Sorry, 1
How
open. 0 open, 1 open.
How it will be?
Sir, 1 upon x minus bracket x will be 1 upon fractional part function of x. So then we know that range of fractional part function of x is 0 close to 1 open. But we know here a fractional part function is present in the denominator part, so it cannot be 0. So 0 will be open and 1 will be also open, range part.
Are you sure?
Yes, sir.
Okay. Now next question is, from the graph you have shown x minus bracket x, that is the fractional part. If the graph is given to you, how we are getting the range of the function? Looking into the graph, you just tell me, if a graph is given to you, how we are getting the range of the function?
Sir, where the line intersects the y-axis, up to that one, we can get the range.
Okay, you please clarify. Your answer is 50% correct. Please once again clarify. It will be better. Now you show that graph that x minus bracket x, you have shown that is a fractional part of the x. That slide you please show. So there you can find the range of the function. Okay.
So this one.
Yes, yes. Now if this graph is given to you, how
Yes,
to
sir.
find the range of the function?
Sir, here the portion that is covered under y-axis, that is from 0 to 1.
Very good, very good, very good. Thank you.
Thank you, sir.
So thank you, Vidya Bhushan.
Thank you, sir.
So can you say what is continuity of greatest integer function?
Sir, continuity.
Is it a continuous function?
Yes, sir.
So it is continuous everywhere. Do you know about when a function is continuous? Do you know?
Sir, I think I don't know.
You see, continuous function. You know what is the meaning of continuous?
Yes.
There is no doubt. So you just look into the graph of your bracket x, greatest integer function, and tell me whether it is continuous or not.
Yes, sir, it is continuous.
It is continuous. It has no break, no breaking point. The function has a jump at each integer. You see in your graph.
Yes, sir. Yes.
It has a jump. 0 to 1, then at 1 there is a jump, then from 1 to 2 there is a jump. That means there it is discontinuous.
Yes, sir.
Okay. So thank you.
Thank you, sir.
Thank you, Vidhu, for your splendid performance. Moving on, we have Stuti Rekha Mahala of class 11, section E. Stuti, please go ahead.
Yes, is my video visible?
Yes, your video is visible.
Is my screen visible now?
Yes, your screen is visible.
Oh, a very refreshing afternoon to one and all present over here, Honorable Principal Ma'am, devoted teachers, and all my dear friends. So today I, Stuti Rekha Mahala, present myself on behalf of the topic Tangent and Cotangent Functions. So as we all are quite familiar with the context of trigonometric functions, based on which we are able to derive a diverse groups of applications and which has its usage nearly in most fields. But today our main areas of concern will be to look into detail about some tangent and cotangent trigonometric functions. So without any further, let's start. Now, tangent function. What exactly is a tangent function? So the tangent function is described over here. From the given diagram, as we can see a right angle triangle for an angle A, the tan function is described as the side opposite to angle A upon the side adjacent to angle A. Now, if we are supposed to deduce the respective sides of a right angle triangle and want to find their values, then we just need to cross multiply the respective parts of the tan function, which is like tan theta is equal to opposite by adjacent. So opposite is equal to adjacent into tan theta. Now let's move on to observe some of the basic properties of a tan function using a unit circle. So let's focus on the animation which has been shown over here. So if the point which was initially lying along the x-axis, if it subtends various angles along moving the circumference, then at different intervals, the values of sine theta and cos theta will change, with respect to which the x and y coordinates of that point will also change. However, we must reckon that the minimum and the maximum values of sine and cosine must be -1 to 1. So following the previous trend of rotational motion we can thus deduce our relation of tan function as sine theta upon cos theta, as one can view from its adjacent diagram, which imitates all the possible values of tan theta in accordance to the unit circle. Now, let's proceed to the tan function graph. So let's look at the graph which has been shown below. So can you all observe the repeating cycles after an interval of pi, or the repeating slopes after an interval of pi, and the asymptotes which are present at every odd multiple of pi by 2? Well, that's because at those specific points, we are unable to find any real values of tan function. Thus, the domain of the tan function is basically all real numbers, excluding all the odd multiples of pi by 2, where n belongs to the set of integers. Whereas the range of the function as the y variation in the graph is from -infinity to +infinity. Now, let's look about some information about cotangent functions. So what exactly is a cotangent function? So from the right angle triangle, we can obtain for an angle x, the cot function is described as a by o, which is the side adjacent to angle X upon the side which is opposite to angle X. And it can also be formulated in terms of sine and cos theta, and it can be represented in this manner, that is cot theta is equal to cos theta upon sine theta. Now let's move on to verify some of the important factors about the unit circle in relation to cotangent functions. So here the adjacent unit circle determines all the possible extent values up to which the cot theta values can be extracted. And this demonstrates exactly some of the very important process which will initially help us to plot our graphs. So following the previous trend of unit circle, we can derive all the respective values for cot function. Now let's plot a difference between the two distinctive graphs, that is the tan theta and the cot theta graphs. Now, can you all observe that from the cot theta graph that there are some very high negative and positive peaks which have been shown as the value of the tan theta approaches to 0? Well, the periodicity of the tan function is similar for the cot function also, that is 180 degrees. So as cot function is the mirror image of the tan function, we can see there is a great slope which falls from its peak as it approaches towards the it falls from its peaks from the 0 degree as it approaches towards 90 degree, and it then repeats into a negative side and it approaches towards a value of 180 degree at and repeats the cycle again. So let's find out the domain and range of cotangent function. Here the asymptotes which are present at the intervals of pi represents that at those specific points we are unable to deduce the relation for any real values. Since the function is undefined at multiple of pi, there are asymptotes at these points. Graphs must contain the dotted asymptote lines. These lines will move if the function contains a horizontal shift, stretch, or shrink. The domain ranges from -infinity to +infinity except for the constant multiples of pi. The range of every cot graph is as similar to that of tan function, that is -infinity to +infinity. So for a quick sum up, let's review the things which we have done. So from the above few slides, we are able to explain as well as got to know about some very important terms and conditions regarding tangent and cotangent functions, which will eventually help us at various events to correlate. The graphs gave us quite conspicuous ideas about the nature of the two functions. The unit circles gave us the idea about the angles of the functions. We discussed some very important minute properties of the respective functions. So now we are all set with the concepts of one of the most important trigonometric functions. Thank you.
Thank you, Stuti. Now I request the judges to please ask their questions.
Thank you, Stuti Rekha, for the energetic presentation. You have mentioned in the last slide about the asymptote. Can you say what do you mean by asymptote?
The asymptotes are those particular line dots which represents that at those exact level we don't have any such real values of x. Means the values of the range, we cannot extract any real values of the range. Sorry, the domain. Sorry.
Can you say what is the asymptotes of tan x?
So it's tan x for every odd multiple of pi by 2.
Every odd multiple of?
Yes, sir.
Pi
By 2.
Yes.
Yes.
You see the gap between pi by 2 and the graph. It tends to 0. The distance between the asymptote and the chord tends to 0 if he moves to infinity.
Yes.
You will close to 0, not 0. The distance
Yes,
is
sir.
there,
It is close
but
to
it tends to 0, approaches to 0. So we will say that type of line is asymptote. Thank you. You have a good knowledge on the integrated portion, that is asymptote. Sai sir, please.
Stuti, you have done nicely about tan and cotan. Now tell me, for what value of theta, tan theta is equal to cot 2 theta?
So, sorry, sir.
Okay, okay, very good, very good, very good. Tan 90 is equal to how much? Is it 1 by 0 or 2 by 0 or 3 by 0?
So tan 90. So, so it's only means 0 it will come.
Okay, very good, very good. Next one. Thank you.
Thank you.
Thank you, Stuti, for this incredible performance. A remarkable presentation indeed. Next, we have Ananya Mahapatra of class 11, section H. All the best, Ananya.
Thank you. I would like to check if I'm visible and audible.
Yes, you are visible and audible both.
Is my screen visible as well?
Yes, your screen is visible as well.
A very good afternoon to one and all present here, esteemed principal ma'am, revered judges, honorable supervisor ma'am, respected teachers, and my dear friends. I'm Ananya Mahapatra of 11H, and my topic for today's math seminar is polynomial functions. Now, before getting started, I would like everyone to have a quick glance on what we'll learn through this presentation. What a polynomial is, what is a polynomial function, the different kinds of polynomial functions and their examples, their degree and standard forms, their graphs, domain and range, and applications. Now, when we hear about polynomial functions, the first question that arises in our mind is what exactly is a polynomial? A polynomial is an expression consisting of variables and coefficients that involves only the operations of addition, subtraction, multiplication, and non-negative integer exponentiation of variables. Some examples of polynomials are given here. Now that we know what a polynomial is, let's move on to polynomial function. A real valued function f from R to R defined by y equals to f of x equals to a0 plus a1x plus a2x square and so on till plus an x to the power n, where n belongs to natural numbers and a0, a1, a2, an all belong to real numbers. For each x belongs to real number is called a polynomial function. For example, p of x equals to 2x square plus 3x plus 1. The image here shows the general form of a polynomial function. Its components are the term, the exponent, the operator, and the constant. The graph of a polynomial function is a straight line parallel to x-axis when n is equal to 0. When n is equal to 1, it is an oblique line. And when n is greater than 1, it is a nonlinear continuous curve. The domain and range of polynomial function depends on the degree of the polynomial. Up next, I have the different types of polynomial functions. Zero polynomial function or constant function, linear polynomial function, quadratic polynomial function, cubic polynomial function, quartic polynomial function, and quintic polynomial function. Here are some examples of the different types of polynomial functions. Linear, f of x equals to 2x plus 5. Quadratic, f of x equals to 6x squared plus 11x minus 35. Cubic, f of x equals to minus 3x cubed plus x minus 6. Quartic, f of x equals to x to the power 4 plus 1. Quintic, f of x equals to x to the power 5 minus x plus 1. Moving on. This table gives a brief preview about the names and general form of the different types of polynomial functions placed against the degree of polynomials. Up first is zero polynomial function. Standard form, p of x equals to a, which is a into x to the power 0. Its graph is a horizontal line parallel to the x-axis, as we can see in the image here, which is the graph for f of x equals to 3. We can see the red line is parallel to the x-axis, which indicates that the output of the function is constant irrespective of the input. Its domain is set of all real numbers, while its range is a singleton set A0. Zero polynomial, a special case of a polynomial of degree 0. Its definition goes by a function f from R to R such that y equals to f of x equals to 0 for all x belongs to R. Its graph is a straight line coinciding with x-axis. Its domain is set of all real numbers while its range is a singleton set 0. Up next is linear polynomial function. Its standard form is p of x equals to ax plus b. Its graph is an oblique line with slope as a and the constant b represents the y-intercept of a line. The image here shows the graph for the polynomial function y equals to x plus 2, and we can see the graph here is an oblique line, the green line. The domain is set of all real numbers, while the range is also set of all real numbers. Moving on, quadratic polynomial function. It is the one we are most familiar with. Its standard form is p of x equals to ax squared plus bx plus c. Its graph is a parabola passing through the origin, where constant a represents the width of the parabola. Whether the parabola faces upward or downward depends on the nature of the a. As we can see in the first image here, it shows the graph for the function y equals to x squared. Its parabola faces upward because the value of a is greater than 0, which is positive. And in the second case, it is the graph for y equals to minus x squared, and the parabola faces downward because the value of a is negative, which is less than a. Thus, we can conclude that if a is greater than 0, the parabola faces upward, and if a is less than 0, the parabola faces downward. The domain of quadratic polynomial function is set of all real numbers, and the range is a subset of R. Finally, cubic polynomial function. Its standard form, p of x equals to ax cubed plus bx squared plus cx plus t. Its graph is symmetric with respect to its inflection point, that is, it is invariant under a rotation of a half turn around this point. As we can see in the image here, which shows the graph for y equals to x cubed, the shape of the graph is something like the blue line, and the inflection point is the origin itself. The inflection point is nothing but a point on a graph where the function changes its concavity. The domain is set of all real numbers because the graph of the polynomial function covers the entire real number line, which is the same for the vertical extent as well. So since the horizontal extent and vertical extent both cover the complete real number line, thus the domain and range is set of all real numbers. Last but not the least, I would like to present some applications of the different polynomial functions. One of the most common application we find is in projectile motion. For example, when we throw a ball into the air and it comes back due to gravity, its height from the ground at a given time t can be modeled with a polynomial function of the form h of t equals to at squared plus bt plus c, where h of t is equal to height of an object at time t. Some other applications are an engineer designing roads, buildings, and other structures as well as in construction. Economists use polynomials to model economic growth pattern in various fields of science, such as in physics or chemical equations. In financial industries to calculate cost, revenue, etc. On this note, I would like to conclude my presentation. Thank you very much and have a great day ahead.
Thank you, Ananya. You put forth a splendid performance. Now I would request the judges to please ask their questions.
Thank you, Ananya. Can you say what is the domain of polynomial function?
So the domain of a polynomial function is set of all real numbers.
Set of real numbers, all polynomial functions. Okay, thank you.
Ananya, am I audible?
Sir? Yes, sir.
So range of x square plus 2, tell me. Range of x square plus 2.
Sir, it would be Sir, x square plus 2, right?
Yes. X
range.
square plus range.
So x square plus 2 would be minus 2 root over of minus 2. It would also be real numbers, I think.
Okay, very good. Very good. Next one.
Thank you, judges. Thank you, Ananya. Great effort. Now we have Janabi Mohapatra of class 11, section H.
A very good afternoon to everyone. Honorable Principal Ma'am, esteemed supervisor, respected judges and teachers, and all my dear friends. This is Janvi Mohapatra, the student of class 11H. Today I am going to discuss something about piecewise function. First of all, what is a piecewise function? A function that combines pieces of different functions. Each piece is for a different domain, which is identified with the set of x values. For example, f of x is equals to the first piece is minus x plus 2 if x is less than 0, and when x is greater than 0, the piece is 3x minus 3. Why are piecewise functions important? In real life, lots of problems are modeled by piecewise functions. Examples: finding shipping costs, income taxes, ordering t-shirts. Here are some different graphs with domain and range, where g of x equals to minus 3, and the domain statement is x less than equals to minus 4 and greater than minus 7. And the next three are mentioned here. The domain of this graph ranges from minus 7 to 7 in closed and open intervals. And the range is from minus 4 to minus 2 in open intervals, union minus 1 to 4 in closed intervals. With the help of this values and domain statements, we can graph it out. Here comes another graph with piecewise functions and in steps, where f of x equals to 1, which is on the y-axis, if the condition will be x is less than minus 3 and greater than equals to minus 4. Here we can graph it out in steps, and the other three are followed. Here comes another graph with 4 pieces, where h of x is equals to minus x by 3, and the condition is x less than equals to minus 3 and greater than equals to minus 6. And the rest 3 follows here. In this graph, the domain ranges from minus 6 to 7 within closed intervals, and the range is minus 4 to 2 in closed interval, union 4 to 7 in open interval. Now moving to the next slide. Now comes step functions. Functions whose graphs resemble set of stair steps are known as step functions. There are two kinds of step functions. One, ceiling function. Second, floor function. An example of a ceiling function is when a phone service company charges by the number of minutes used and always rounds up to the nearest integer of minutes. In a floor function, all non-integers are rounded down to the nearest integer. An example of a floor function is we round our age down to the nearest year and do not add a year to our age until we have passed our birthday. Here comes an example of a graph on the basis of step function, where f of x is equals to 1 on the y-axis, and the condition is x less than 1 and greater than equals to 0. Similarly, the other three are graphed out here. So we can see the stair steps in this graph. So it is identified as step function. Now comes piecewise function, which is of two types, continuous and non-continuous. In continuous function, the domain ranges from negative infinity to infinity within open interval, and the range 0 to infinity in open interval. And in non-continuous function, the domain is R or minus infinity to infinity in open interval, and the range is R or negative infinity to infinity in open interval. This is the graph of continuous function, and this is the graph for non-continuous function. Today's last slides of my presentation is some of the art integrations on piecewise functions. This is an amazing function with the help of which we can create different types of art integrations or diagrams. Thank you.
Thank you, Janavi. Now I request the judges to please ask their questions.
Thank you, Janvi, for the presentation.
Thank you, sir. Good afternoon, sir.
Good afternoon. Can you say what is the continuity of modulus of x? Where it is continuous or where it is not continuous?
Sorry, sir. Can you repeat the question?
F of x is equal to modulus of x. What do you say about the continuity of this function?
It continues till infinity.
Continuous at infinity. Can you say what is the structure of the graph? This looks like what?
It's on the negative side of x-axis.
So this is, there is another name also. This is for what? Modulus function f of x over mod x. This is V shape. Okay.
It's B.
Sai sir, please.
Yes. Janhavi, am I audible
Yes,
here?
sir. Yes, sir.
2.3 close bracket. What is the value? 2.3 close bracket. Output is how much? Okay, no issue.
Sir,
Next one.
3.
Thank you very much. 3. Is it 3? Are you sure?
Yes, sir.
Okay.
Yes, sir.
It actually 2. 2.3 close bracket is equal to 2. Okay. Okay. Thank you.
Thank you, sir.
Thank you, Janavi. Thank you, judges. That was a scintillating performance coming from you. Now, let us move on to the next performance by Gul Sharma of class 11, section H.
Pure mathematics is in its way the poetry of the logical ideas. Mathematics is not about numbers, equations, computation, or algorithm. It's all about understanding. Good afternoon, everyone, honorable judges, respected supervisor, ma'am, knowledgeable teachers, and all my dear friends. Today, I, Gul Sharma, is representing you the topic logarithmic function. So let's start. First, we need to understand what is actually logarithmic function. So if a is greater than 0 and a is not equal to 1, then the function defined by f of x equals to log x to the base a, where x is greater than 0, is called the logarithmic function. We have learned that the logarithmic function and the exponential function are inverse functions. That is, log x to the base a equals to y, which is also known as x equals to a to the power y. We observe that the domain of the logarithmic function is the set of all non-negative real numbers, that is from 0 to infinity. And the range is the set R of all real numbers. As a is greater than 0 and a is not equal to 1, so we have the following cases. The first case that we have is when a is greater than 1. In this case, we have y equals to log x to the base a, which is less than 0 for 0 is less than x is less than 1, which is equals to 0 for x is not, where x is equal to 1 and is greater to 0 for x is greater than 1. Also, the value of y increases with the increase in x. Here in this graph, it represents a is greater than y. Here we can see in the graph that the line passes through x-axis at intersecting at 1, 0. Next, we have case 2 when 0 is less than a is less than 1. In this case, we have y equals to log x to the base a is greater than 0 for for 0 is less than x is less than 1 is equal to 0 for x is equal to 1 is less than 0 for x is greater than 1. Also, the value of y decreases with the increase in x. Here in the graph, we can see the representation of 0 is less than a is less than 1. Here, the graph intersect at x-axis at point 1, 0. Now we have the different properties of logarithmic functions. The first property is log 1 to the base a equals to 0, log a to the base a equals to 1, log xy to the base a equals to log module x to the base a plus log module y to the base a, log x by y to the base a equals to log module x to the base a minus log module y to the base a. Next property we have log x to the power n to the base a equals to n module x n log module x to the base a. Next property log x to the base a equals to 1 by log a to the base x. For log x to the power m to the base a to the power n equals to m by n log x to the base a. Next property we have x to the power log y to the base a, that is equal to y to the power log x to the base a. Next property we have if a is greater than 1 and then the value of f of x is equal to log x to the base a increases with the increase in x. That is x is less than y, that is same as log x to the base a is less than log y to the base a. Also, log x to the base a is less than 0 for 0 is less than x is less than 1 is equal to 0 for x is equal to 1 is less than 0, so is greater than 0 for x is greater than 1. If last property, if 0 is less than a is less than 1, then the value of f of x equals to log x to the base a decreases with the increase in x. That is x is less than y, which is similar to log x to the base a is less than log y to the base a. Also, log x to the base a is greater than 0 for 0 is less than x is less than 1. is equal to 0 for x is equal to 1 and is less than 0 for x is greater than 1. Next, we have graphs of different logarithmic functions. The first graph that you see over here represents the log sine x. Here in the graph, we can see that the line touches to the x-axis at pi by 2 and it touches the y dash axis at -3. The second graph we have is about, it represents about log x squared. In this graph, you can see that the line represents y equals to log x to the base 2. The next graph that we have represents these many equations where x equals to -2, x equals to -2. Dark blue line represents y equals to 5 log into x plus 2. The orange line represents y equals to log x plus 2 and red line represents y equals to log x. So this is the end of the PPT. I hope you liked it and thank you for your patient hearing.
Thank you, Gul. Now I request the judges to please put forward their questions.
Thank you, Gul Sharma. Can you say what is the domain of log of x minus 1? Log of x minus 1.
Yes, sir. So can you repeat, please?
Log of x minus 1. The domain of this function.
So it's a non-negative real number.
Is defined for 0.
So it will lie between 0 to infinity.
So 0 not included.
So 0 included.
So log of x minus 1 is defined for the x 0.
So sorry?
Is the function is defined for x equal to 0?
Yes, sir.
You just put x as 0. See what happens. Log 0 minus 1. Okay. Thank you. Sai sir, please.
Gul.
Yes, sir. Good afternoon, sir.
Good afternoon. 2 into log 10 base 10. How much?
Sir, 2
Write
into?
down. 2 into log 10 base 10.
Yes, sir.
How much?
Sir, it's 2.
Very good.
Thank you,
Very
sir.
good. Next.
Thank you, Gul. It was really amazing. Now I would call Ritikesh Mandal of class 12, section D, to start his presentation. Ritikesh, please.
Good afternoon, everyone. Honorable teachers, respected principal ma'am, esteemed judges, and all my dear friends. This is Ritikesh Mandal from 12D, and today I'll be discussing the graphs of sec inverse function and cosec inverse function and describe its properties as well. So without further ado, let's just jump right into it. So here is my first slide, and this is my topic. And before moving towards the main topic, let's have a look what an inverse function graph looks like. So on the left, as you can see, this is the graph of g of x, and on the right, there's the graph of g inverse x. If you notice closely, both of them look symmetrical, and that symmetry occurs when we draw a line x equal to y, which looks something like this. The red one is the g of x, and the blue one is the g inverse x. And as I said, both of them are a reflection of each other about the line x equal to y. And some points to keep in mind when we are talking about inverse trigonometric functions is that if the graph passes the horizontal line test, what does that mean? It's that if a line is drawn parallel to x-axis and if it touches the graph at a single point, then only then that graph will have an inverse function. If it touches more than 2 points, then that graph will never have an inverse function. Secondly, if there is a point as a comma b on the graph of f, then there will be a point as b comma a on the graph of f inverse. And as I said, f inverse is a reflection of the graph f about the line x equal to y, and all inverse trigonometric functions are bijective functions. So moving to the main topic is the cosec inverse graph. For a moment, ignore whatever is written on the left and observe the graph closely. You will see that the graph starts from negative infinity and goes all the way till -1. And there is no graph between the interval -1 and 1. And then the graph continues from 1 and goes all the way till positive infinity. Hence the domain is -infinity, -1, open and closed respectively, union 1, infinity, closed and open respectively. Have a look at the y-axis as well. The graph lies between -π/2 and goes all the way up till +π/2. But there is no graph at fx equal to 0 because cosec inverse x equal to 0 does not exist. Hence the range is -π/2, +π/2, both closed, minus the element 0. Let's talk about some properties of this graph. As you can see, it is a decreasing graph and it is an odd function graph. And it is an odd function graph, which means that if f of x, if there is f, which means is that if it is f of -x, it is minus fx. And it is aperiodic in nature, which means it does not repeat after itself over a certain interval. It is a bounded graph. And when x is positive, the graph lies in the first quadrant. And when x is negative, the graph lies in the third quadrant. Let's move on to the next one, is that we observe some form of interesting observations, is that on the left we have the sine inverse x and the right we have cosec inverse x. If you put both the graphs all together, we will form a pattern, we will form a figure which looks something like this. Hence we can say that where the sine inverse graph starts or ends, the cosec inverse graph continues itself and vice versa, forming a complete picture. On the next we have, hold on a second. Yes, on the next we have the graph of sec inverse x. Again, ignore whatever is written on the left and observe that the graph starts from -infinity and goes all the way till -1. But there is no graph between the interval -1 and 1. And then the graph starts once again and goes all the way till positive infinity. Hence the domain is -infinity, -1, open and closed respectively, union 1, infinity, closed and open respectively. Let's have a look at the y-axis as well. The graph lies between 0 and goes all the way till +π. But there is no graph at fx equal to π/2. There is no graph at π/2. Hence the range is 0, π, -π/2. Let's have a look at the properties as well. It is an increasing graph. As you can see, it is increasing. It is neither or nor even function graph. And it is aperiodic in nature, means it doesn't repeat after itself over a certain interval. It is a bounded graph for the domain it has. And when x is positive, the graph lies in the first quadrant. And when x is negative, graph lies in the second quadrant. Again, the trend is followed here as well. On the left, we have the graph of cos inverse x, and on the right, we have the graph of sec inverse x. When we put both these graphs all together, put it in the right way, we will form a figure which looks something like this. Hence, we can see here as well, where the cos inverse x graph starts or ends, the cosec inverse graph continues and completes the picture perfectly altogether and fits it perfectly. Hence, of all this, I would like to conclude that of all the inverse trigonometric functions, the graph of inverse trigonometric functions, when put together with their respective inverse reciprocal functions, they form a complete picture and hence perfectly fit into each other. I would like to take your leave. Thank you very much for your patience.
Thank you, Ritikesh. That was an outstanding performance from your end. Now I request the judges to please ask their questions.
Ritikesh?
Yes, sir.
Sec inverse x is equal to 1/sec x. What about your opinion?
Sir, that is not possible.
Very good.
Yes.
Next to Amyo, sir.
Okay, Rishikesh, thank you.
Thank you, sir.
Can you say what is the principal value of cosec inverse -2?
Sir, can you repeat?
Cosec inverse -2.
Cosec inverse -2. So what about it? I repeat it once. So I can't hear you properly.
Principal value.
Cosec inverse -2. Sir, can you repeat it once again? Sorry about that.
What is the principal value of cosec inverse minus 2?
Sir, principal value, it will lie between 0 and pi. So,
Okay, thank you.
This was the last performance of the day. Now I would request you all to give a huge round of applause for all the participants and their efforts to put up such amazing presentations in front of us. This seminar has been a mix of great performances which gave us amazing insights. It actually ended up on a good note. And now that we have seen the amazing and unparalleled presentations by the participants, let's ask our Honorable Principal Madam to speak a few words and enlighten us. Due to some unavailable circumstances, ma'am had to leave. So I request Gayatri ma'am to speak a few words.
Good afternoon, everyone. Here I am going to announce the result of this seminar then. Thank you, students, for your nice performance. And here the first position goes to Anirudh Pradhan, class 12, section E. Then second position is backed by Vidhu Bhushan Patra, class 11, section E. And third position is backed by Anjali Mishra, class 11, section A. Congratulations to all the participants and the winners. Thank you, everyone.
Thank you, ma'am. My heartiest congratulations to all the winners as well as the participants. So now I would like to deliver the vote of thanks. I, Inakshi Das of class 12A, on behalf of JV Public School UNIT-VIII, would like to thank our Honorable Principal Ma'am for organizing such a beautiful virtual event. I take immense pleasure to thank our Supervisor Ma'am for her graceful presence. My heartfelt gratitude to the judges of the seminar, Mr. Amir Ranjan Mohanty sir and Mr. Sai Shankar Acharya sir, for their auspicious presence and for encouraging the participants. I'm happy to express a vote of thanks to all our maths teachers for making the seminar a grand success through their guidance and unconditional support. My sincere thanks to Diptendu sir and Niranjan sir for conducting this virtual event so successfully. A very big thanks to all our participants for presenting their work so beautifully on the virtual platform. I would like to thank the coordinators of this event for making this seminar a grand success. Finally, I thank the audience for your patient hearing. Without your cooperation, the event would not have been possible. Once again, I thank you all for your cordial support and for making this event a memorable one. Thank you.